Hello students, myself XII-Sci Gorane from XII-Sci RBNB College Sriampur. I am junior college teacher in physics. Today we are going to study wave optics, sub-articles in the chapter wave optics. You know interference of waves, the modification in the intensity of light produced due to superposition of two waves is an interference. And in interference, if the waves are in same phase, the interference is constructive, and if the waves are out of phase, the interference is destructive. In interference of light waves, at constructive interference we get bright fringe, and at destructive interference we get dark fringe. Bright and dark fringes are produced alternately in the interference pattern. You also know the diffraction of light, the bending of light round the edges of obstacle or slit and entering into the region of geometrical shadow is the diffraction. You have studied all these two concepts, interference and diffraction. Today we see what is the difference between interference and diffraction. Interference and diffraction. What is the main difference between these two? In interference is the interaction of light coming from two different wavefronts. From two coherent sources. This is interference we know. Diffraction is interaction of light waves coming from different parts of same wavefront. Different parts of same wavefront. This is also interaction of light waves. But it is coming from different parts of the same wavefront. In interference, fringes are of same width. Fringes, we call it as also bands, are of same width. But in diffraction, fringes are not of same width. Fringes are not of same width. Width of the central bright fringe or central maxima is twice the width of secondary maxima or minimum. Here intensity of bright fringe or bright fringes is same. Intensity of bright fringe or bright fringes is same. In interference, in diffraction, intensity decreases intensity of bright fringes decreases. Intensity of bright fringes goes on decreasing as order of fringes increases. As order of fringes increases. Width of the central bright fringe is maximum. Intensity of secondary maxima goes on decreasing, whereas here intensity of all bright fringes is same. In interference, dark fringes are perfectly dark. Dark fringes are perfectly dark. Whereas in diffraction, dark fringes are not perfectly dark. Dark fringes are not perfectly dark. So these are the some distinguishing points between interference and diffraction. Now we see the next article, that is the optical path. Optical path. The equation of light wave traveling in a vacuum along x direction is given by the equation E is equal to E0 sin kx minus omega t. This is the equation of light wave traveling in vacuum along the x direction. E0 is the amplitude of that wave. This kx minus omega t is called as phase of the wave. K is wave vector. K is called as wave vector. And omega is angular frequency of wave. Kx minus omega t is phase of the wave. E0 is the amplitude. And this is the equation of light wave traveling in vacuum along the x direction. This wave vector k is omega upon v, where this v is speed of the wave. V is speed of wave. If light wave travels a distance delta x, if it travels a distance delta x, its phase change delta phi is given by delta phi is equal to k into delta x. Phase change is delta phi is equal to k into delta x. But we know k is equal to omega upon v. So this delta phi is omega upon v delta x. But for vacuum, we write this v as equal to c. Velocity of light in vacuum we denote it by c. Hence we write the equation delta phi is equal to omega upon c into delta x. Suppose this is equation number 2. Now if this wave is traveling in a medium of refractive index n, this is the wave traveling in a vacuum. In vacuum, instead of we write a speed of light as c, and we get the phase difference or phase change delta phi for the part delta x as delta phi is equal to k delta x. K is the wave number omega upon v. But for the vacuum, v is equal to c. So this delta phi is omega c into delta x. For the wave traveling in vacuum, traveling in a medium of refractive index here, for wave traveling in a medium of refractive index here, n is the refractive index of the medium, wave vector suppose k dash. Suppose wave vector is k dash and this k dash is omega upon v. But v is c upon n, so this k dash is c upon n. N is the absolute refractive index of the medium, we know, and this n we know it is c upon v. For the wave traveling in a medium of refractive index n, suppose wave vector k dash is omega upon v. If n is absolute refractive index of the medium, then it is velocity in vacuum upon velocity in medium. So this v is c upon n, and hence this k dash is omega n. Wave vector k dash is omega n upon c. If the wave travels distance delta x in the medium, if the wave travels a distance delta x in this medium, phase difference delta phi dash, similar to this equation, phase difference delta phi dash will be k dash into delta x. But k dash is omega n upon c, so this delta phi dash omega n upon c into delta x, phase in the medium. But this n delta x we substitute as delta x dash, so we write delta phi dash omega upon c into delta x dash, where delta x dash is, this delta x dash is n into delta x. This delta x dash we write it in place of n into delta x. Hence we say that part of delta x in a medium of refractive index n, part of delta x in a medium of refractive index n is equivalent to path length of n delta x in vacuum. Here we say that path length of delta x in a medium of refractive index n, it is equivalent to path length of n delta x in vacuum. And this n delta x is called as optical optical path traveled by the wave. This is the optical path traveled by the wave. Path difference of delta x in the medium is equivalent to path n delta x in a vacuum, and this n delta x is optical path traveled by the wave. Hence, that optical path is n delta x. Optical path is equal to n delta x. For vacuum or in vacuum, we know for vacuum n is equal to 1. So this optical path will be delta x, and this is nothing but the actual path. For the vacuum, we consider refractive index as 1. If we substitute here n as 1, this optical path equal to delta x, that is optical path is equal to actual path. Optical path is equal to actual path. So from this formula we say that optical path is equal to refractive index. Here is the refractive index multiplied by distance traveled by the light in medium. Distance traveled by light in medium. From this equation, optical path is equal to refractive index multiplied by distance traveled by the light in the medium. Hence, this optical path in medium can also be defined as corresponding path in vacuum. It is the corresponding path in vacuum that light travels in same time as it takes in given medium. See again, optical path in a medium can also be defined as it is the corresponding path in vacuum that light travels in same time as it takes in given medium. That is the optical path. As we know, the formula time is equal to distance upon speed. Time is equal to distance upon speed. We know this formula. So in medium, we write T as distance in medium upon speed in medium. As we know, time is distance upon speed. In a given medium, we write T as distance in medium upon speed in medium. For the vacuum, we write the same formula as distance in vacuum upon speed in vacuum. In the same time, this is the formula for the distance in medium upon volume in medium, and during the same time, distance in vacuum upon velocity in vacuum. If we equate these two, or from these two, we write distance in medium upon velocity in medium is equal to distance in vacuum upon velocity in vacuum. But optical path is the distance in vacuum. Optical path is the distance in vacuum. Therefore, distance in vacuum is equal to velocity in vacuum upon velocity in medium into distance in medium. But this is nothing but the refractive index of the medium. Velocity in vacuum upon velocity in medium is the refractive index of the medium. Hence, this distance in vacuum we call it as the optical path. Is equal to refractive index into distance in medium. Optical path is equal to refractive index into distance in medium. So distance d in medium of refractive index n, distance d in medium of refractive index n introduces a path difference equal to n d minus d. That is the optical path minus that distance in the medium, and hence that is equal to, if we take d as common, path difference is d in bracket n minus 1. Distance d in medium of refractive index n introduces a path difference nd minus d. Nd is the optical path. So it introduces a path difference that is equal to d n minus 1 over a ray traveling equal distance in vacuum. Over a ray traveling equal distance in vacuum. This is the path difference. Now this is about the optical path. Now two waves interfere constructively, or their interference is constructive if their optical paths are equal. Two waves interfere constructively, or there is a constructive interference if their optical path lengths are equal. Optical path lengths are equal, then that waves interfere constructively and we get the bright fringe, or their optical path differs by integral multiple of wavelength. Two waves interfere constructively if their optical path lengths are equal, or their optical path lengths differ by integral multiple of wavelength. Now in Young's double slit experiment we know, if suppose this S1 and S2 are the two slits, and we observe the interference pattern here. Suppose this P is any point on the screen. This S1P, this is S2P, and this is the central point. This O is the supposed central point. At these points, this S1O is equal to S2O. In Young's double slit experiment, we know this is the screen. S1, S2 are the two slits. They produce the interference pattern on the screen. O is the central point on the screen. At O, this S1O distance is equal to S2O path lengths are equal, they interfere constructively and we get a bright point here. And at point P, that is bright or dark, it depends on the path difference between the waves reaching at this point. If this path difference is integral multiple of wavelength, we get the bright point. If this path difference is odd multiple of wavelength, we get the dark point. And this point is always bright because this S1O and S2O, these distances of path lengths are equal. But if we introduce transparent plate of thickness T, transparent plate of thickness T and refractive index N in front of this slit S1, if we place transparent plate of thickness T and refractive index N in front of this slit S1, before introducing this plate, this S1P is smaller than S2P. But after introduction of the plate, transparent plate of thickness T and refractive index N, this S1P path length is more than this S2P. And there is optical path difference between them as N minus 1 into T. Optical path difference between the waves will be N minus 1 into T. After introduction of this plate here in front of S1, before the introduction, these two path lengths are equal. Here we get the bright fringe, and on both sides we get alternate bright and dark fringes. But if let us introduce here, this path length will be greater than this S2O. Hence, as path lengths are different, the bright spot is not observed at point O as before, but it appears at different point other than O, where path lengths are equal. Bright point will not be obtained here because by the introduction of the plate, this path length will be more than this. Condition of brightness is not satisfied. This bright point is not obtained here, but at a different point, their optical path lengths are equal. It means this central bright point is shifted, and as this point is shifted, the interference pattern will be also shifted in one direction. This point will not be here, it is shifted due to the introduction of the plate. Bright point will be obtained where the path lengths are equal. And on both sides of that bright point, where it is shifted, on both sides of it, we get alternate bright and dark fringes. It means by the introduction of that plate, the fringe pattern will be shifted. Now we see one example or one problem related with that optical path. We know optical path, and we see one problem related with that optical path concept. The problem is like this. Optical path of ray of light, optical path of ray of light optical path of ray of light of given wavelength wavelength is given, traveling a distance of 3 centimeter, traveling a distance of 3 centimeter, traveling a distance of 3 centimeter in flint glass, of refractive index 1.6, same as that, on traveling a distance x centimeter, through a medium, of refractive index 1.5, through a medium of refractive index 1.25, determine the value of x. Optical path of ray of light of given wavelength is not given here, but particular wavelength, we say particular wavelength, traveling a distance of 3 centimeter in a flint glass of refractive index 1.6, same as that optical path is same as that of traveling a distance of x centimeter through a medium of refractive index 1.25. We have to determine the value of that x. Now that first distance we consider it as d1. Suppose d1 is 3 centimeter. d1 is 3 centimeter. That is 3 into 10 raised to minus 2 meter. And first refractive index is n1, and that is 1.6. Now the next distance is x. And second refractive index is 1.25. This is our given data. And we have to find the value of x. We know optical path is refractive index into distance. We know optical path is equal to refractive index into distance. For the first case, optical path will be n1 d1. Optical path will be n1 d1. Suppose this is equation 1. For the second case, optical path will be refractive index into distance. So for the second case, optical path will be n2 into x. For the first case, optical path is refractive index into distance, that is n1 d1. For the second case, optical path will be refractive index into distance. We know this formula. Already we have studied it. But it is given that optical paths are same. Hence, comparing that 1 and 2, we get optical path is same. So this N2x that will be equal to N1 D1. And hence this x will be N1 D1 divided by N2. Our N1 is 1.6. D1 is 3 into 10 raised to 2 minus 2. And our N2 is 1.25. So this x will be, this product will be 4.8 upon 1.25 into 10 raised to minus 2. And by solving this, solve this by using the logarithm, we get value of x as 3.84 multiplied by 10 raised to minus 2 meter. 3.84 into 10 raised to minus 2 meter, or we write it as 3.84 centimeter. Okay, we stop here. Thank you.